This is video 18 in the Thermodynamics course with Lars-Erik. This is about calculation of G excess over RT from binary data. This is from the beginning of chapter 12, and the data, they are from table 12.2. The G excess over RT for a binary mixture is the sum of the mole fractions and the logarithms to the activity coefficients. So if we can measure the mole fractions in the liquid, then we only need to find an expression for the activity coefficients to calculate the G excess. And the data from table 12.2, they contain data for MEK, which is component 1, and TOL, which is component 2, and these are at 50 centigrade. This MEK is actually methyl ethyl ketone. You do not need to know about the chemistry in such a component. Perhaps you have heard about toluene, but it is not important what are actually the chemicals, but that there are two components which we can call component 1 and 2. And in the table we have the pressure, we have the liquid mole fraction of component 1, and we have the vapor mole fraction of component 1. And in the textbook there are several data points. I have 4. And we start with mole fraction 0, that is that it is only component 2, and then the pressure, it has been measured to 12.30 kilopascal. And these fractions are measured quite accurate. It is actually quite difficult to measure a mole fraction in a gas this accurate.
Excuse me, K is ketone?
That is ketone. Yeah. We have a second mixture point. So when we change the mixture composition, then we also change the pressure. And we go to mole fraction 1.0, then we have pure component 1. And then we have a pressure of 36.09 kilopascal. And to get a picture of this is that we have a chamber that is closed, and we have a liquid, and we have a gas, we have a temperature, we have a pressure, we have mole fraction of component 1, mole fraction of component 2 in the vapor. We have the same temperature and pressure in the liquid, and we have the liquid compositions x1 and x2, and then the temperature is kept constant, either by a water bath or by electricity, or the temperature is kept constant, and then some way the pressure and the compositions are measured in some way in this chamber. Then we start, it is in a way not necessary, but I like to start to calculate the ideal pressure for all points. And by ideal pressure, that is following Raoult's law. The ideal pressure is x1 times P1 saturated plus x2 times P2 saturated, and the saturation pressure is the pressure we had for a pure component, and we are operating at 50 bar, so we can read the saturation pressure from this table as the endpoint pressures. So this is actually the saturation pressure of component 2. When the mole fraction of 1 is 0, then the mole fraction of component 2 must be 1. We have pure component 2, and then that pressure is P2 sat. And on the other end, we have pure component 1. The pressure has been measured to 36.09, and then that is the saturation pressure of 1. And this could also have been taken as a check if these pressures were very different from the saturation pressure found from a handbook or something. Then we knew that something was wrong with the experiments, so this could be a test of that we are actually measuring reasonably. So, ideal pressure at the point of point 1981 is the mole fraction of component 1 times the saturation pressure of component 1, that one, plus 1 minus 0.1981. This is a binary system, so x2 must be 1 minus x1. That is 7.22. And the ideal pressure for the mole fraction of 0.7934 is 0.7934 times the saturation pressure plus 0.2066 is 1 minus that one. And we multiply with the saturation pressure of component 2, and we get 31.70. And then we compare this to the experimental pressures. These are from experiments, and 18.61, and this is 31.75. So then we get the impression that these measured pressures, they are close to ideal pressures, but not exactly equal to the pressures. So this is a close to ideal liquid, but it is not an ideal liquid. Then we actually calculate the activity coefficient as the pressure times Y1 divided by the saturation pressure times X1. This is an extended with an activity coefficient with ideal gas. The fugacity coefficient is close to 1. These pressures are well below 1 atmosphere, so we can assume that the gas is ideal, and this is the Raoult's law extended with activity coefficient, and it can be looked as a correction factor. And then we calculate gamma 1, or the activity coefficient for component 1, to be 18.61 times 0.4565 divided by 36.09 times 0.1981, which is 1.90. And gamma 2, or the activity coefficient of component 2, is calculated the same way. The pressure times the mole fraction in the vapor, which is 1 minus 4565 divided by the saturation pressure of component 2 times 1 minus 0.1981, and that is 1.025. And then we can also calculate the logarithms of the activity coefficients. If this was to be ideal, this should be 1 and this should be 0. And then the task was actually to calculate the G excess over RT. And the GE over RT for the point of 1981 is 0.1981 times 0.173 plus 0.19 times 0.025, and that is 0.054. And in a way, it is not so this is a number we do not have much feeling for, but actually we now have calculated the G excess over RT. Then I go on with an example of a G excess model or an activity model. And this is the Margil model, where the GE over RT is A21 times x1 plus A12 times x2 times x1 times x2. This is equation 12.9. And the logarithm to the activity coefficient is then x2 squared times A12 plus 2 times A21 minus A12 times x1 and similar, it is symmetric for gamma 2. So the Margil model is an example that of a model that tried to express the G excess over RT as a function of composition. And in that case, the activity coefficients can be calculated using these equations. Then regression of the data in table 12.2. Gives A12 equal to 0.372 and A21 equal to 0.198. That is, if we take all the data we have, and in the textbook the number of measured numbers are much larger, the G excess over RT can be calculated for many points. Then there is performed a regression. Then it is a numeric optimization of A21 and A12, which are the parameters, so that the difference between the experimental GART and the model GERT is at an even. And then that gives these two parameters. And then, again, these parameters can be used to calculate the ln gamma by my GIL model. For any x1 and x2 and then for especially for x1 equal to 0.1981, x2 equal to 0.8090. That is actually this point. Then ln to gamma 1 for this case is 0.8019 squared times 0.372 plus 2 times 0.198 minus 0.372 times 0.1981, and ln gamma 1 is then 0.195. We can compare that to the experimental 0.173. I feel more comfortable with the activity coefficient. That is what I regard as the correction factor. That is 1.2 15. The experimental is 1.190. So the model predicts the activity coefficient quite well, not extremely accurate, but by these parameters it is possible to calculate an activity coefficient that is quite close to the experimental value. And this is just to test. What is more important is that this model can be used to calculate the activity coefficients for any composition. So this is the end of the video. Thank you.